Monday.
Oh my god, that was so much fun.
Yeah, it's just.
I'm doing that.
That was
It was just fun. I was hanging out with like people.
I was over at 9:45.
Actually, we're a bunch of cheapos.
Where's the chips? I gotta pull through $100. 3 bags.
My friend Audrey has $1,000 to neighbors bumpers. Here, this is for that little group.
People just give you chips, they just give you their money. You're like, why are you taking chips? You're special. They just want you on the list. It was ridiculous.
So you made money on it?
No, it was like, not for us. It's a
Charity
charity
event?
event.
I mean,
No, it's like for, it's for Carriage House.
Right.
For what is it, for votes or they were just like?
But the votes don't really work as dancers. Take the money.
all of
yeah,
them
I
rich
know.
people that
But
just throw stuff.
Barely.
You're kind of a horrible person sometimes.
I agree.
But it's kind of funny.
I don't know what's the other one who noticed.
I didn't think there were.
Andrew walked away saying, did you know rich people here are really fun? I was like, wow. Okay.
Let me just throw a few things up here. Remember, if we're naming a covalent molecule, the first molecule that's listed is stated just as the element that it is, unless we have multiple of it. In this case, we would have dinitrogen. The last element, even if there is only one atom, is given a prefix, monoxide. Dinitrogen monoxide. Also remember, this is a general fact about covalent bonding. It's always between a non-metal and a non-metal. And it always involves the sharing of electron orbitals. You get used to, over time, looking at the atoms in terms of their valence electrons when you talk about making molecules. For example, like oxygen. Oxygen has 6 valence electrons. You start with 2 in the s orbital and then 1 in each of the p orbitals, backfilling for the additional p orbital. You end up with 6 valence electrons. And what that basically gives you is 2 bonding sites. There's 2 spots where if I were sharing this electron with an electron from a neighboring atom, then I would have 8 electrons to oxygen's name. He would satisfy the octet rule. And that's where a molecule like water comes in. Because hydrogen's sitting there saying, man, if I just had an additional electron, I would have 2 electrons. That's all I need for the octet. And when you connect the dots, you're showing a shared pair of electrons, each line for a single shared pair. Remember, if we have nitrogen, I'm going to draw him mirror imaged, just so that I can pull this off easily. It looks like, when you look at nitrogen, you see like 3 bonding sites. Because if I just paired up each of these electrons, I would then have 8 electrons to nitrogen's name, 2 exclusively to nitrogen, and then 3 pairs shared. Well, when nitrogen bonds to itself, it can just bond to itself 3 times to satisfy the octet rule. We call that a triple bond. The electrons that are not involved in the bonding we call lone pairs. Okay. Let's look at carbon for a second. Because carbon, if you look on the periodic table, carbon is in group 4. So that means carbon has 4 outermost electrons. And if you go to make a dot structure for this, you're going to put 2 electrons in the s orbitals, and then 2 electrons in the p orbitals, 1 in each. Now, if you look at this though for a second, you're like, wait a second. It looks like there's 2 bonding sites. Because if there was a bond here, and there was a bond there, we would get closer to the octet. But notice, if carbon would act like this, it actually wouldn't be able to have an octet. It would have 2 to itself, and then 4 in those shared regions. That would still, even if carbon bonded twice, that would still only be 6 electrons, which would be not an octet. It would seem like carbon would have an impossible time of forming an octet, which that would be crazy, because that would mean that carbon would never be able to covalently bond with anything. Yet we know that carbon covalently bonds with things. We've seen CO2 and CO, and for that matter, C6H12O6, right? You know carbon covalently bonds. And in fact, carbon covalently bonds with a lot of things. So what's up with that? Because if we look at carbon just as it is, or as we would expect it to be, even if it bonds at its 2 bonding sites, it ends up not satisfying the octet. So what does carbon do? It does something that's referred to as hybridization. It exhibits this behavior, hybridization of electron orbitals. We are used to, carbon has, let's look at carbon's electron configuration for a second. Because carbon has, 6 electrons? Yeah, 6 electrons. So its first 2 electrons are in its 1s orbital. The next 2 electrons in the 2s orbital. And then if you go out to the 2p, you're going to have 3 of those. 2 in the 1s, 2 in the 2s, 2 in the 2p. That's what you expect. And that's what we demonstrated with our dot structure. And we noticed how even if you share these 2 orbitals, you're still 2 electrons short. That's no good. And you know, if you were looking at the second energy level, I'll do my best drawing here, you'd have a sphere for your 2s. And then in the x direction, you'd have a 2p. In the y direction, you'd have a 2p. And in the z direction, you'd have a 2p. So if you look at the second energy level in terms of the actual physical orbitals, you'd have a 2p in the z direction, a 2p in the y direction, a 2p in the x direction, as well as a 2s as a sphere with it. This is not how carbon responds, how carbon reacts, how carbon is, however. And that's because of this thing called hybridization. If you think of when you talk about what a hybrid is, like a hybrid of, I say hybrid, you think car, cars that, what? What makes a hybrid a hybrid? Yes. A hybrid is not an electric car. It's not a gasoline car. It's a combination of both. Carbon does not use s orbitals, it does not use p orbitals, it combines them both. That's what the hybridization of carbon is. And as a result, when you look at carbon and its 6 electrons, this is what should happen in theory. This is what should happen. What we drew up above. We should have a carbon with 2 s electrons and 2 p electrons. That's what we should have. But here's what actually happens in practice, or in reality. Here's what actually happens. Carbon has a 1s orbital with 2 electrons. Carbon's s and p orbitals in the second energy level hybridize to form not a 2s orbital, not a 2p orbital, or not 3 2p orbitals, but rather 4 sp orbitals. So rather than forming 1s and 3p orbitals, the orbitals hybridize and form 4 sp orbitals, each of the same energy. These hybrid orbitals are all the same, and we know that whenever we have orbitals of the same energy, the electrons will fill in one at a time. So, the 4 electrons that are remaining will each go into one of these sp hybrid orbitals. The shape of the sp hybrid orbitals, if you were curious, one of them is above the atom, and then 3 of them are down below. It almost looks like kind of like a tripod. It's making all 4 corners of a pyramid. Here's one of your sp orbitals, here's another, here's another, here's another, going off in all 4 directions. But that changes the dot structure for carbon, doesn't it? Because rather than having 2 in the 2s and 1 in each of 2 p's, carbon has 1 in each of its sps. Why does it do this? I don't know exactly why. I don't know what compelled carbon to act like this. But I do know that if carbon was like it should theoretically be, carbon would bond to nothing. Because even if it would bond to things, it still wouldn't have an octet and it wouldn't be satisfied. It could never be satisfied. With the hybridization, it can bond to many things. It has 4 bonding sites. That gives you a lot of flexibility. If you look at the number of covalently bonded carbon-based molecules and compare it to all other molecules combined, the number of carbon-based covalent molecules is greater. Let me say that again. If you compare, if you look in put in one hand the number of carbon-based covalently bonded molecules, and in the other hand put all other molecules combined, covalent or ionic or otherwise, the number of carbon-based covalent molecules is greater. The sp hybridization, the 4 bonding sites, gives it an enormous amount of flexibility in bonding. So, what if we had something like this? CH4. Now, when you see carbon in a molecule with 2 nonmetals, this is covalent, you're going to draw your carbon with 4 dots, one on each corner. Because anytime you see carbon, and you'll see carbon a lot, I just told you that there's more carbon-based covalent molecules than there are all other molecules combined. You'll see it a lot. When you see it, draw it with these 4 bonding sites. So, carbon has 4 bonding sites. Hydrogen each has 1. There you go. Carbon tetrahydride would be the name of this guy. He actually has a more common name than carbon tetrahydride. He goes by the name methane, for short. This is the natural gas that's burning in the furnaces of the school and probably of your house. Notice carbon with 4 bonds, 2, 4, 6, 8 electrons, octet satisfaction. What about CO2? What about CO2? You know your carbon has 4 bonding sites. And each of your oxygens in group oxygens in group 6. So it's got 6 valence electrons, 2 in the s and 4 in the p's. That leaves 2 bonding sites. Connect the dots. I can have an oxygen over here with 2 bonding sites as well, and connect the dots. Now that looks kind of ugly the way that I drew it. if I redraw it to balance out the molecule, I'd have a carbon in the middle, 2 bonds to the right to an oxygen with 2 lone pairs, and a carbon with 2 bonds to the left with 2 lone pairs. Now you might wonder, maybe you're wondering, maybe you're not. When I drew this carbon dioxide molecule, I drew him straight like a bar. And when I drew, however, whenever I drew my water molecule, I drew him bent, like a V. You might wonder, why did I do that? There was good reason. And it's able to be deduced. Because the question would be, why don't I draw carbon dioxide like that? It can easily be explained. Each line represents what? Shared pair of electrons. Electrons are negatively charged. This pair, electrons, negatively charged. Over here, these 2 dots represent electrons that are negatively charged. Now, you tell me what happens when you get negative charges around negative charges. They repel. They get as far apart from each other as they possibly can. Now, if you look at this oxygen, he's got 2 electrons here, 2 electrons there, 2 electrons here, 2 electrons there. They're going to spread out as much as possible, and they're basically going to take 4 corners of a square, basically. And it's in 3 dimensions, so it's technically not going to be 4 corners of a square, but as we draw it, it basically appears as such. Because these 2 electrons are going to be repelling those 2 electrons, and these 2 electrons, those 2 electrons, and they're going to be repelling. And you're going to get a configuration like so. Here, you have 2 electrons going one way, 2 electrons going the other. Why wouldn't it go like this? I mean, well, why would it form an angle why would it form an angle this small when those pairs of electrons could get as far away as possible? And for those 2 pairs of electrons, or 2 pairs in each case, those 2 bonds, to get as far away as possible, the most spread out they can get is to be on either side of a line. So you're not going to form something like this, because the negative charges are going to repel each other and form a straight line. You'll find this bent structure will only exist when the center molecule has lone pairs. And if the center molecule does not have lone pairs, then you'll just spread out as much as possible. So, but the thing to think about is the shape is dictated by the electrons repelling each other. I don't want to get too much into detail on shape because it's really a very nitpicky exercise, and it's really not something that first-year chemistry students get a lot into. But I want you to have a thought behind it to say, because if I asked you a question, why does carbon dioxide line up in a straight configuration whereas water does not, you should be able to explain it in the sense that we have lone pairs trying to get as far apart as they can from the non-lone pairs, and over here we've got 2 bonds trying to get as far away from each other as possible. And with no lone pairs in the way, those bonds can get as far away as they possibly want, which would be on either sides of the line. But the big why are those bonds trying to get as far away as possible? Because those bonds involve electrons, and electrons are all negatively charged, and thus they're going to be repelling each other. Okay, so that's, should we do another example? I mean, we can, I'll give one more example of carbon. C2H6, I think this will work, C2H, yeah, C2H6. And to start here, start with your carbons, each with 4 electrons. I'm going to tell you, just to start, that the carbons are bonded to each other and you can see then where everything else fits in. I'll just start us off here, because this wouldn't be one that would be even on the test, but this is one that we can just get more practice with carbon. Remember, when you draw a dot structure for carbon, 4 dots. Hybridization. Why? I don't know exactly why, but it does it. And the fact that it does it gives an enormous variety of possibilities. Each of these bonding sites, there were 6 of them, is going to bond to a hydrogen with a single bond. Hydrogen's then satisfied. Hydrogen will always only have a single bond attached to it. Think about it. Hydrogen only has 1 energy level. Hydrogen will want 2 electrons. 1 bond will give it 2 electrons, therefore it would never want more than 1 bond. Carbon will always have 4 bonds. Why? It wants an octet. It has 4 bonding sites. It's going to want to make 4 bonds. When you look at oxygen, he's always going to have 2 bonds, or at least he often have 2 bonds. Let me show you an example. This is when you start to deal with covalent bonding, you can deal with some exceptions, like carbon, and I'm going to draw another exception here in a second too.
Do all the atoms, like elements with 4 valence?
Do sp3 hybridization, or sp hybridization? Not sure. The only one that you really need to care about is carbon. Yeah, it doesn't make mention, the book doesn't make mention of other molecules. Carbon's really the only one that you encounter a whole lot. So that's all we'll deal with at this point. Let us talk about one last thing. Resonance. Resonance occurs when a covalently bonded molecule could exist in multiple configurations. So resonance occurs with covalent bonds that could exist in multiple configurations. Okay, I'm gonna, oh boy, yeah, we can do this. I'm gonna try my best to draw this out. And an example of a chemical that exhibits resonance that can exist in multiple configurations is sulfur dioxide. That's an example, sulfur dioxide. Now, each of these are in group 6. Oxygen, 2 bonding sites. Sulfur, I tell you what I'm going to do. The 1 oxygen I put his electrons with dots. The sulfur, I'm going to use X's for his electrons. I know that's funky, but just bear with.